Alright, moving on to section 7.4, we're going to look at solving exponential log equations. We're going to look at some pretty basic equations today, but it's still going to be important for us to grasp the concepts of solving the equations today for when we get to the more difficult problems. So we'll look at multiple ways to solve a lot of these equations. A couple of the properties we want to recall, well obviously all of the properties, but specifically a to the x equals a to the y if and only if x equals y, and log base a of x equals log base a of y if and only if x equals y. Also remember a to the log base a of x is x, and log base a of a to the x is x. Okay, so first one, solve for x, 3 to the x equals 27. So pause the video and solve this. I want you to come up with 2 different methods to solve it. So pause it, come up with 2 different methods, unpause when you're ready to check your work. Okay, so here I'm showing you 3 different thought processes or approaches to this problem. They're all correct. You do not have to do all of them. There are still other approaches as well. These are just the 3 maybe most obvious. So the first one over here on the left, what I'm doing here is I'm recognizing that 27 can be rewritten as a base 3, and it's 3 cubed. So I know 3 to the x equals 3 cubed. Well, now from my property that we looked at on the last slide, remember right here, a to the x equals a to the y if and only if x equals y, I know that x has to equal 3. Okay, that's the simplest way. Another method, rewrite the exponential equation as a log equation. So this is what we're going to end up doing more often than not. So rewrite the exponential equation as a log equation, so I know x equals log base 3 of 27. Now, because 27 is a power of 3, I could go right from here to my answer. However, if 27 was not a nice power of 3, then I would have to use the change of base formula. So I chose to use natural log. You could also use log base 10. But I know natural log of 27 over natural log of 3 equals x. If I typed that into my calculator, I'd get x equals 3. Another approach is to take the log of both sides. In this case, I chose natural log. So I can do the natural log of 3 to the x equals the natural log of 27. Because of my properties of logs, I can bring the x down in front. So x times natural log of 3 equals natural log of 27. Divide by the natural log of 3, x equals natural log of 27 over natural log of 3, so x equals 3. Again, there are still other approaches. So if you came up with something different, that's okay. Alright, next one. Solve for x, 2/3 to the x equals 4/9. Again, I want you to come up with 2 different methods. One of them hopefully different than one of the methods you used last time. Alright, so on the left here I used the same technique that I did first on the previous problem. So 2/3 to the x equals, I recognize that 4 and 9 both have a base of 2 and 3 respectively. So 2/3 squared. Therefore, I know x has to equal 2. Okay, so again, that's the simple solution, but that only works when these share a common base. So then the next thing I did was, instead of taking the natural log of both sides, or rewriting this as a log equation, I took log base 2/3 of both sides. So log base 2/3 of 2/3 to the x equals log base 2/3 of 4/9. Bring the x down in front, and I have x times log base 2/3 of 2/3. But log base 2/3 of 2/3 is 1. So this side just becomes x, and log base 2/3 of 4/9 is log of 4/9 over log of 2/3 using the change of base formula, which equals 2 then. Alright, next one. Solve for x. Again, try to come up with at least 2 different methods to solve. Pause the video, unpause when you're ready to check your work. Okay, so on the left here, what I did was I brought the natural log of 5 over to the other side of the equation, and then from my property I recognize that I have a log with the same base on both sides and nothing else. Therefore, x has to equal 5. That's again the simple way. Another thing I could have done is combine the logs on the left. Because they have the same base and they're subtracted, I can combine them into a single log with division. So this becomes the natural log of x over 5 equals 0. Now turn this into an exponential equation to get rid of the log. So x over 5 equals e to the 0. E to the 0 is 1. Multiply both sides by 5, I get x equals 5. This method here in the middle is what you're going to have to do sometimes. So you want to make sure you're at least comfortable with that. It's not always going to be as straightforward as just setting two logs equal to each other. So you want to know how to change a log to an exponential and an exponential to a log. Now, another thing, when we're solving log equations, we have to check for extraneous solutions. So you need to make sure that if you plug x back in, that it does actually work in the original equation. It's very important that it's in the original equation. I'll show you an example in class tomorrow about how, depending on which method you use to solve, you can create extraneous solutions accidentally. Next one. Solve for x, pause the video, unpause when you're ready to check your work. Alright, this one step. Change it from an exponential to a log equation. We get x equals the natural log of 4. If you want to type natural log of 4 into your calculator, that's okay. On a test or a quiz, I'll be very specific on whether I want exact answers. Remember, this is an exact answer versus rounding to 3 decimal places. Another thing to point out, when we have exponential equations, we do not have to check for extraneous solutions. So assuming we solve correctly, we will not create extraneous solutions with exponential equations, only with log equations. Alright, next one. Solve for x. Pause the video, unpause when you're ready to check your work. Alright, so here, change it to an exponential equation to get rid of the log, so x equals 5 to the negative third, which is 1 over 125. If I plug that back in, it's going to work. Really what we're checking for when we're checking for extraneous solutions when it comes to log equations is making sure that what we're taking the log of is not a negative. So that's the type of extraneous solution that we could possibly create. So I don't actually have to plug it back in, do the change of base formula, and type it into my calculator to see if I get negative 3. I just need to make sure that when I plug this back in here, I'm not taking the log of a negative. So in this case, I'm good. Next one, solve for x. Pause the video, unpause when you're ready to check. Okay, so here I'd accept either the red or the green. Our first step though is isolate the exponential. So we divide by 2, 5 to the x equals 16. Now I chose to convert this to a log equation. You could have taken the natural log of both sides, log base 10 of both sides, log base 5 of both sides. Any of those methods would work. So I end up with x equals log base 5 of 16. So that's correct, or I can say x equals natural log of 16 over natural log of 5, or log of 16 over log of 5, or type that into my calculator and get a decimal equivalent. Next one, solve for x, pause the video, unpause when you're ready. Alright, so here I chose to isolate the exponential again first. That's whenever we have an exponential equation, if there's a single exponential term, that's what you want to do. You want to isolate the exponential. If there are multiple exponential terms, you want to try to combine them somehow or factor so that you can isolate each term individually. So divide by the 8, I get 3 to the 6 minus x equals 5. Now here I chose to take the natural log of both sides. Again, just to show you different techniques, that's the only reason why I'm doing this. If you did something else, that's okay. Then I can bring the 6 minus x down in front, divide by natural log of 3. This becomes algebra now, so x equals 6 minus the natural log of 5 divided by the natural log of 3. Again, you could type that into your calculator if you want, or you can leave it like that. It's more important right now that we understand the process of solving. Alright, last example. Log base 9 of 4 plus x equals log base 9 of 2x minus 1. Pause the video, unpause when you're ready to check your work. Okay, so the simple way to solve this is to recognize that I have a single log on the left, a single log on the right, no other terms, and the same base. Therefore, I know that what I take the log of has to be equal. So remember, that's our property. So 4 plus x equals 2x minus 1. Solve that. X equals 5. Check to make sure if I plug 5 in here, I get log base 9 of 4 plus 5, which is 9. That's good. Here I get log base 9 of 2 times 5, which is 10, minus 1, which is 9. So that's good. So neither one of those are negative. It's not extraneous. Now here's a longer method, which again, it's important that you understand this process though, because some problems you might have to do this. So here I subtracted the log base 9 of 2x minus 1. Combine these two logs into a single log with division. Change it to an exponential. So that's the green. 9 to the 0 is 1. Multiply both sides by the least common denominator, and now I end up with the same equation that I had before. Solve and I get x equals 5. Okay, another one, not too bad, 10 minutes long. So the key thing we want to understand, again, these were all basic equations. They will get more complicated, so if we understand the basics and multiple techniques for the basics, then the more complicated ones will be that much easier. So when solving exponential equations, we want to isolate the exponential if possible. Then rewrite it as a log, take the log of both sides, use the one-to-one property, whatever is easiest, and solve for x. When solving logarithmic equations, isolate the log if possible. Then rewrite as an exponential or exponentiate both sides, or use the one-to-one property to solve for x. Don't forget with logs, check for extraneous solutions.